Would you like to introduce your students?
Sure. I forget, who did you have listed first in the schedule?
It doesn't matter either. Neither. I just said student talks. I didn't list anyone first.
Fair enough. Okay. So I guess let's start with Terrence. Since he's going to be, I just talked about an evolution code, a code to solve an initial value problem. And Terrence has been working very hard on creating a code that solves Maxwell's equations using two different formulations in the electrovacuum in the Einstein toolkit using NURPY to generate essential pieces of that code. So without further ado, I introduce Terrence.
Thanks. Can everyone hear me okay?
I can hear you great. Would you mind sharing your screen? Oh, great, thank you.
Yep. One second. Okay. Yeah, so we just heard Zach talk about solving like the scale wave equation, like generating ETK thorns. So here I'll just give a quick demonstration of solving Maxwell's equations in vacuum with ETK thorns generated by NURPY. And just a quick mention, Patrick Nelson wrote a lot of the base Jupyter notebooks, and I've just been working on those since then. Okay, so to motivate our discussion about Maxwell's equations, I'd first like to talk about like hyperbolicity of PDEs. So the basic idea of hyperbolicity is just like the notion of wave-like behavior for numerical solutions. And the idea is that if you have a weakly hyperbolic system of PDEs, then you might have error modes, which will kind of like sit in your numerical domain and just add error to your results. And they just sit there because they're zero speed, so they're not propagating away. And a really nice example of this was in the 3+1 decomposition of Einstein's equations. For like when that first happened, like using the ADM formalism, and it turned out that formalism was weakly hyperbolic, and it led to a lot of instabilities to the point where you couldn't really evolve those equations for a long time. So it turns out that system of equations was weakly hyperbolic, but then later on we had the BSSM formalism, which turned out to be strongly hyperbolic. So in analogy, here we'll just be talking about two different formalisms of Maxwell's equations, where system 1 is going to be weakly hyperbolic or ADM-like, and system 2 will be strongly hyperbolic or BSSM-like. So we start off with the evolution equations, and we're solving Maxwell's equations in vacuum and in flat space and Cartesian coordinates. Again, this is just a demonstration, so just keeping everything simple. So on the left-hand side, we have the evolution equations of the fields, and you'll notice that we're evolving the vector potential instead of the magnetic field, and that's just to guarantee that the divergence of the magnetic fields always stays down to Rondorf error. We're also working in Lorentz gauge, and so we have this gauge evolution equation for the scalar potential, and on the right-hand side we have the constraint equation, and this comes from Gauss's law. That since we're working in vacuum, there are no sources, and so the divergence of the electric field should be 0. But again, this system of equations is weakly hyperbolic because if you look at this term and you compare like this second derivative to the derivatives that you see in the wave equation, it's a mixed second derivative, so it's not wave-like at all. And we'll see that does lead to like worse behavior of the errors. So to deal with this kind of error, or to deal with that kind of error, we'd like to introduce a new evolution variable that can make the equations more wave-like. So we call this variable gamma, and we define gamma as the divergence of the vector potential, and that leads us to system 2, which turns out to be strongly hyperbolic or BSSM-like. So on the left-hand side, again, we have the evolution equations, where boxed we have these modified equations. And on the right-hand side, we have another constraint equation where we can monitor how well like how well our errors adhere to the definition of gamma. Okay, so we have our evolution equations. Now we need initial data. So here we just define a toroidal dipole field solution. It's pretty simple. So what we'll do is that we'll just define the initial data at t equals 0, and then we'll just march the solution forward in time with finite difference, like with the evolution equations and so on. So now that we have our evolution equations and our initial data, we need boundary conditions. So to really see whether or not these error modes propagate, we'll use a radiative boundary condition or the Sommerfeld boundary condition. And the basic idea is that it just assumes a spherically symmetric wave with some radial fall off. And again, we want to see those waves just propagate through that transparent boundary. And this leads to minimal reflections. And if you'd like a more detailed derivation, please see NERPY's Sommerfeld tutorial, which Zach and I wrote. Okay. So now we'll generate, so now I'll just talk about like how we generate the E to K thorns. So as Zach mentioned before, NERPY just generates highly optimized C code from really readable tensorial expressions, which allows us to minimize human error, so like bugs and so on. And we use the freely available SymPy package in Python. And again, all the thorns are fully documented. And these 2 thorns will be updated soon on the NERPY page. Yep. Some more details on the thorns. Again, they're heavily documented. And as Zach mentioned before, the CCL files are either like totally automatically generated, like the param.ccl file, or they're easily built from templates. I've been using the Baikal template, which I think itself uses Maclaurin or Lean, one of those. And they're both the thorns, the initial data thorn and the evolution thorn, they're written such that at runtime you can choose different options for initial data. Right now we only have the toroidal dipole fields initial data, but maybe we might add others. We're still thinking about it. And then for the evolution equations, it also outputs 2nd, 4th, 6th, and 8th order finite differences. So in the param file, in the par files, you can just choose whatever finite difference you want, and you should be good to go. Okay, and this is show everyone like how easy it is to do this. On the left hand side, and on top we have like system 1, where you can see that like you can match the indices and the equations like pretty easily to each other. So whether you're working with like vectors or tensors, and you'll notice there's kind of like subscript D, capital D down, and it just corresponds to like derivatives.
Just a second, Terrence. We have a question for you from a mad scientist.
Oh, okay. Can you read it or?
No, it's they raised their hand. The mad scientist, your question?
Hey, I'm sorry, I raised my hand when Zach was giving his talk, and
I'm sorry, I didn't see it.
yeah, no
I,
problem.
I just saw it now. Okay.
Okay, yeah. Yeah, so again, you'll see this underscore, this got underscore DD, and that just corresponds to these derivatives. Ideally, if you're working in curved space-time, then we would introduce the metric tensor to like make things a little bit more formal. But here we're just in Cartesian coordinates and flat space, so we can get away with like these kind of notation. So you can imagine that like if you're coding these up, then you'd like to have a LaTeX. You have a LaTeX block, and then you'd have the equations. And in fact, this is what it would look like. So up here, you have these equations, and then right below, you can just start coding in these equations. And you could imagine a scenario where you're coding up like a really huge equation, and you could just like code it up in blocks. So you have like block 1, you code that up, block 2, etc. And it makes it really nice and really easy to follow. So once I did all that, then we can just run everything within the Einstein toolkit, where we monitor the L2 norm of the constraint violation. And I was really pleased to know that and the Einstein toolkit does have like reductions. So here we just use a norm 2 reduction, which makes things really easy, I think. And so we monitor this constraint. And so on the left-hand side, you have a plot from Knapp, Walker, and Baumgart from 2002 for system 1. And here we use iterative Crank-Nicholson time stepping plus fourth order finite differencing. We don't get exact numerical agreement, but we do see the qualitative agreement. Whereas system 1, which is weakly hyperbolic, you see these non-propagating or zero mode error modes, zero speed error modes, and they're just staying there. Like, yeah, they're staying there, adding error to your simulation. And zooming in, you see that there is initial behavior, but it just settles down to some constant value. Now compare this to system 2, where we do see we do see these error modes propagate away at the speed of light, and you do see the L2 norm of the constraint violation decrease exponentially. And if we zoom in a little bit, you'll see that it does increase a little bit more than what you see in system 1, but again, it decreases exponentially, so no worries there. So in summary, we've just written and documented all these ETK thorns that provide like a really nice demonstration of hyperbolicity of Maxwell's equations. And more importantly, we've confirmed similar qualitative behavior to Knapp, Walker, and Baumgart, specifically the propagation of error modes. In the future, we'd like to add functionality for spherical coordinates, and we'd also like to generalize to curved spacetime to like do some interesting projects with this, like for example, like super radiance with black holes. And we're considering maybe adding other initial data options. And that's my talk. Thank you.
Virtual applause. Thank you, Terrence. Are there any questions for Terrence? Okay, I don't see any questions. Oh, go ahead.
Sorry, I didn't raise my hand. So a question for you. For this thorn, do you see it being coupled to some type of ideal MHD code as well to use as a way to model, say, the Maxwell field outside of a neutron star or things like that?
I'm not really sure. I think Zach and I are still deciding on different projects to work on. Does that answer your question? Sorry, again, this was just a demonstration to like just show how NeRPy can be used to generate these ETK thorns. In terms of actual science, I don't really know.
No, the answer is fine. The answer we're still deliberating is fine. Thanks.
Yeah. Next question, Eric Schneider.
Hi, Terrence. Can you point again to the URL to the Python notebook?
Yeah. So there. Oh,
You could just paste it in the chat. That would be ideal.
Oh yeah, I could do that.
That would work. Thank you. Yes.
Yeah. They're not updated to what I'm using now, but they will be soon.
Okay. Thank you.
All right. Thank you, Terrence. Zach, would you like to introduce Patrick?